So, hi everyone. uh, Before we start, if you have any doubt like why anyone should use Shyft, so I just want to share with them one thing, and it's this. So, as a Solana developer, you're already a Saiyan, but with Shyft, you can very easily go Super Saiyan. So that's how we basically tell. It's like a Solana developer with superpowers. So yeah, before we start, let me just walk you through what we'll be doing today. Um, we'll be talking about minting compressed NFTs. So compressed NFTs is the talk of the town, and we're not gonna dive too much into the nitty gritties of how compression is implemented in Solana, but rather than how you can mint, transfer, burn compressed NFTs without having too much underlying knowledge about it, and with just one API call or a one SDK call from our SDK. Yeah. So, but just for people who may not be much aware about compressed NFTs, the core difference lies in one single thing. That is, the compressed NFTs metadata is not stored in an account on chain. Rather, it is just stored in your logs, in your, you can say, in your ledger data. And what is this ledger data? It is basically your transaction data. So if we see any compressed NFT, you will see that their metadata is just right there in, as a parameter. But for a normal NFT, that metadata has an actual account address, an account space is allocated for it, and whoever is creating that space needs to pay rent for that account space, and only then the on-chain metadata is stored. But with compressed NFT, this step is completely removed. Hence, you don't need to pay the account rent anymore. But at the same time, there's a slight drawback that with normal NFT you can just call any RPC, get account info, and you'll get the account info. You see, deserialize it, and you have the metadata with you. But in terms of compressed NFT, since it is not stored on chain, there is no account data. And if you fetch any um, compressed NFT address, so for example, this is a compressed NFT address on DevNet. And if we check it, say on SolScan, you won't find anything. Yeah, it has zero sol. It basically doesn't exist. But so here's the catch. So basically, you have to rely on certain indexers who are basically listening on the bubblegum protocol, which is the protocol that mints compressed NFT, and then they have to see, okay, a new compressed NFT is minted, and then they have to store it in their off-chain storage in their own databases. So this is one thing that you have to rely on. And another thing is that for normal compressed NFTs, for normal NFTs, you can see the entire transaction history, who's bidding on those NFTs, who's listing those NFTs, who's transferring it from one wallet to another. But in this case, since the it's the address which is deterministic, because it's kind of the same way you create a PDA of few deterministic things and you'll get an address, but it is not stored on chain. So you cannot track the transaction history, that okay, it was listed here, then someone transferred it from one wallet to another, these kind of things. um, so yeah, these are some of the differences. Wait, let me see why it's not working. So if we just search for bubblegum, which is the compressed NFT, you can see like the NFTs are being minted and being transferred. And for example, if we see an NFT mint, mm, here, and if you see the transaction, you will see that the metadata is here in the transaction. It's right here. But the same metadata for a normal NFT is on chain. That's the core difference that I just wanted to get across. And yeah, let's start with some, with minting some compressed NFTs. But before we do that, we need to create a Merkle tree. And a Merkle tree is, I'm not going to go into nitty gritty of what a Merkle tree is, what kind of data structure that is, but the core part is that it's a tree, and the hash of all the branches and all the leaves of that tree is stored on chain. And that's why you don't have to pay any rent. That's why it's so cheap, because you don't have to store all the NFTs metadata, all the account information on chain. No, you just have to store the hash of all the leaves of all the branches on chain. That's it. And so for minting compressed NFTs, you have to first create a tree, and then basically you add leaves to it. And that whole tree is basically your compressed NFT collection, you can call it. Yeah. And we'll be focusing on two major things here. One, seeing that how easy it is to create Merkle trees, mint compressed NFTs to it. You can add collection information, you can transfer, you can burn your NFTs, and at the same time, we'll also be indexing our tree. So you can call it as a, so we are calling it compressed NFTs plus indexer. So let's just call it compressor. And what we're going to do is we're going to monitor our tree that we have created, and then whenever there's a mint that is happening on that tree, basically whenever a new leaf is appended into it, we will monitor it and we will store it off chain. And this is basically how uh, other RPC providers are also doing it. So yeah, it's not foolproof, of course, but it's a proof of concept which we can play around with. And to monitor our Merkle tree, we'll be using Shyft callbacks, and we'll be storing it in a Postgres database. We'll be using Superbase for it, which very easily helps us set up a database. And we'll run a very simple Express server for it. Okay. So without further ado, let's actually deep dive and let's create a Merkle tree. Okay, so we have, we are working, we'll be working on DevNet, and this is my wallet address. Then you have max depth. Max depth is basically, what's the depth of the tree. Basically, what's the max distance that a leaf can be added from root to, what's the last index where it can be added. And you can just do two, whatever you use here, you can just do 2 raised to power max depth. That's the depth of your tree. To actually understand these things, I would suggest just use this compress.app. And you can see, for example, if you want to mint. So yeah, this is one another thing, that once you create a tree with these parameters, it's fixed. The depth is fixed. So only, you can add only these many compressed NFTs to the tree. And depending on the parameters, it will also tell you like how much do you need to pay to create this tree. And the initial mint, you can see, will be a bit high, but adding more and more leaves will be negligible. So let's just do a very simple one. Let's just take these values, and we're going to come here. Let's add 20, then it's 64 and 0. Okay, 64 and canopy depth is 0. And while creating the tree, if you're doing it in your front end, and basically maybe you're just exposing this and you want someone else to pay the actual fee, you can specify the fee pair. If not, whoever is the wallet address will be basically paying the fee. And so let's create a new tree. And this API, basically just one API call, and you get an encoded transaction back. Now all you need to do is just sign this encoded transaction, and a tree will be created for you. Right now we have this small utility tool that we have created. You enter the encode. Oh, sorry, my bad. It's wrong here. Neat. Yeah. And you just specify the, so it's costing us 0.31 sol. And that's it. A Merkle tree has been created for us. And so this is a very small utility tool where you connect your wallet, you enter the encoded transaction, and then you can sign it. And we can verify this on the translator, which is simple to read Solana Explorer. And you can see that a create tree has been created. This is the Merkle tree address, tree authority, pair, buffer size, and max depth. And yeah, we'll copy this so that we can now start minting NFTs into this tree. And that's our next API, mint compressed NFT. So I'll be the creator wallet. This is our Merkle tree address, and you can specify the metadata URI. We're just using the Mad Lads metadata URI here. You can specify your own metadata, and if you want, if you know how to create a new metadata, you can. We have an API for that. Create metadata, and you add some information here, and a metadata is created for you, and it is also uploaded to IPFS. So, for example, if I run this, I'm not sure if it will. Okay. So we should be getting an IPFS link here. But anyway, so we'll just use this metadata URI, and which is MadLads. Merkle tree is delegate authority. Basically, you want to keep, if you want to delegate the minting authority to someone else, you can do that. This is the collection address. If you want all the NFTs of your Merkle tree to belong to a certain collection, you can specify here. Now there are certain prerequisites for this. One, that it needs to be a master edition NFT. It cannot be an edition NFT. And second, it needs to have a max supply of one. Basically, it needs to be a unique NFT. And if it is such NFT, you can specify it here. And then your max supply primary sale is mutable, and then you have the main thing, which is receiver. You can either mint it to your own wallet, or you can mint it to someone else. So now you can think about creating compressed NFT dispensers, compressed NFT airdrops, stuff like that. And if you want someone else to pay the fee for this entire transaction, you can specify the fee here. If not, you can this is optional parameter, you can remove this as well. Now let's try to mint some NFTs, compressed NFTs. And again, we'll just make a one API call. We got the mint address, and now all we need to do is just copy this again. We'll come here. Where is our Shyft insider? We'll paste our transaction, submit. And done. We have successfully minted a compressed NFT. Congratulations. And yeah, here's the MadLad. It's showing MadLad because we used a MadLad metadata URI. And you can see it is minted to this user, and it is the Merkle trees here. Here's the tree authority, here's the fee pair, and yeah, you can actually see it here. Okay, so now let's try to transfer this recently minted compressed NFT, which is here. We'll copy this address. Let's try to transfer this from one wallet to another. And it's as simple as just specifying the NFT address, sender, and receiver. So if we check this, we can see the owner address is this. We'll copy. Yeah. This is the sender, and I'll just use my own wallet here. Yeah, and that's it. To try this, let's see. Okay, we got the encoded transaction, and let's try to sign it. And oh, sorry. So now this wallet is not sending, while the other wallet is actually sending. So we need that wallet sign, which is this one. So I'll just select again, and I'll try to submit it again. I hope the block hash has not expired. Yep, done. And we successfully transferred Yep, compressed NFT transfer. This is the NFT address. It's transferred from this wallet to this wallet. Awesome. And you can see that it's very easy to understand the transaction also. Tree authority, Merkle tree. So now if you see, if you check this, there's no transactions. For a normal NFT, you would see all the transactions that are happening, right? But on this it's no, there's no transactions. But we can indeed check the tree, because the tree is on chain, right? And the tree should have the transactions. Oh, sorry, it's underneath. Yep, we can see this tree was created, a compressed NFT was minted into the tree, and then the compressed NFT was transferred. So now this is all good, but say you are creating your own project, and you are actually not interested in all the compressed NFTs that are being minted throughout the world. You're only concerned about the compressed NFTs that cater to your system, to your project. So basically, you need to index them. I mean, you can use some other third party as well, but you can very easily index your own compressed NFTs as well. So you don't have to rely on other third parties. And by the way, similarly, we have a burn compressed NFT here. You can try this out. Just specify the NFT address, wallet address, and that's it. The NFT will be burned. I'll leave you guys to experiment around it. But let's come here. So let's just leave this. So what we are doing here is two things. Yeah. One, we're going to specify a tree which we want to index, so that whenever any transaction happens on that tree, we monitor it. We see if it's a compressed NFT min, transfer, or burn, and we update our database accordingly, so that later on, when we want all the NFTs of a particular tree, we can just do this. All the NFTs, mention the tree, and we get all the NFTs. And you can fetch by owner as well. By you have all the metadata also. You can specify by attributes, collection ID, whatever you want. Okay. And how are we going to do that? And that is where the magic of callbacks come, which you might also know about callbacks as webhooks. So let's just check. Uh, okay. Yeah. So we're going to be creating we have already created a small, I'm gonna delete this. This is just super base, and we have created a simple schema to index our compressed NFTs. We just note down the Merkle tree, the NFT address, metadata of the NFT address, and who's the current owner of that NFT. And right now it's empty. So the magic should start once we start indexing it. And if we call this index tree, and if we specify the tree address, which let's use the tree that we just created. It's this one, right? No, sorry. Mm, yeah, I think it's this one. Yep. Yeah, this one, right? So let's just copy this, and let's try to index this tree now. And all we need to do is just specify the tree address. And so in the backend, what's going to happen is we're going to create a callback. And just to show you, how to create a callback, let me just show you in code. Yeah, all you need to do is just you npm install the Shyft SDK, Shyft to -js /js, and then you initialize the Shyft SDK with your API key and the network that you want to operate in, and then that's it. You have a Shyft client, and then you come here, Shyft client.callback.register, and this is optional if you have already specified the network, and you just need to specify the accounts. You can specify multiple accounts, an array of accounts in one single API call. and the callback URL. And the callback URL is the URL where you will get webhooks whenever a certain event happens. Right now, we are not specifying any event, but you can. And what kind of events do we support? It's actually a ton of events. So we support events across NFT, DAO, and DeFi ecosystem. So if you, here it is. So if you want to track NFT mints, token mints, creation, transfers, any kind of marketplace activity, any kind of lending protocols activity, any kind of AMM activity, or DAO realms activity, you can track all of them here very easily. And yeah, so we'll be creating a callback for all the events, and then yeah, you'd be thinking, wait, this is running on localhost. How will an actual Shyft server that is connected to internet will route our, will send us a post request here? And that is where this magic comes in. We'll be using a local tunneling software. We can use Sergio. And what this will do is it will expose our localhost 3000 port to internet. And let's check it out. Come here, this, and it will give me a special URL on which my local host will be exposed. You can use Servio, you can use ngrok, in multiple options out there. Okay, yeah. Let's try again. Yep, got it. Okay. And now if we try to go here, we open this link. Yeah, hi Encode Club, we are building a compressed NFT indexer. Okay. And yeah, so our local host is now exposed on this particular URL. All we need to do is just update this in our environment variable. So this, and tree monitor, and tree monitor is the main function which will get called whenever a transaction on our Merkle tree happens. And yeah, so first thing first, let's actually start indexing our tree. This is useless. I need to go. Okay. And all it does is nothing. It just creates a start callback, and which is this. It creates a callback, and then it sends us the response. Okay. And yeah, let's try. Okay. Now this is our callback ID. You can store it in your database separately if you want to start, stop. You want to programmatically add more addresses to it, delete some addresses, modify the callback URL, modify the event. So you can programmatically basically keep on monitoring the Solana blockchain. And now whenever a transaction happens on this address, we should get a callback URL on this link. And yeah, let's see if that happens. And yeah, before that, whenever we get a callback, tree monitor, we are basically monitoring for 3 events right now, which is compressed NFT mint, NFT transfer, and NFT burn. And we are going to find the action. So there could be multiple actions. So the response structure of the callback is not like your raw Solana transaction. That is where the magic of our transaction parsing comes in. What we do is we identify, okay, what was the type of this transaction, so that we append a type to the transaction. But we don't just stop there. We go ahead and enrich the response with relevant data also. So if you want to check our response structures, they're right here. This is the basic response structure. Actions is an array. But if say someone, an NFT bid happens, all you need to know is like who's the bidder, in which currency, which marketplace, what price, and what NFT address. So you don't have to go ahead and make extra calls to the RPC or to identify the transaction structure to understand, okay, how do I extract relevant information from an NFT bid? Similarly, from burn, listing, uh, liquidity, DAO, you name it, you will get relevant information for the relevant type of transaction, so that it's very easy for you to play around with different events. So for us, we are more interested in compressed NFT mint, and this is the structure that we are returned. And if you see in our database, we are storing Merkle tree, NFT address, metadata, and owner, and we get all of this here. Merkle tree, who's the we get more information. You can modify as per your requirements, but for the simplicity of this POC, we'll just be storing Merkle tree, NFT address, owner, and metadata. And similarly, we have for transfer, we have for burn as well. And yeah, so whenever a compressed NFT mint action happens, we're gonna call handle mint. All we're going to do, all we're doing in mint is just creating this structure and storing it in our database. So, okay, I think everything's done. Let's actually try to mint now. Same thing, we got the encoded transaction. We'll go ahead and sign it. Wait, who's the signer? It's different. The different wallet. So I need to disconnect. And yeah. Okay. Now I can sign. Yep. Done. This is the transaction. Got it. But more importantly, let's see if we got a callback here. And yeah, here it is. This is the callback that we got, compressed NFT mint action. Here, compressed NFT mint action. And then, this is all the information that we got as a callback response. And now let's check our database if it's updated or not. Yep, here you go. You have the Merkle tree, you have the NFT address, metadata, and the owner of the NFT. And this is like a mini DAS API for you, where you are monitoring your tree and you're storing it in your database. And then now, if we go ahead and fetch, let's fetch all the uh, NFTs of this particular tree. Where's the tree address again?
Sorry, Ish, could you zoom in a little bit? It seems like people are having trouble reading the actual code.
I'm so sorry. Yeah. So we'll open source it. I'll put it in a GitHub repo so that everyone can check it out. But yeah, is this better?
Yes, I think this should work fine. Thank you.
Okay. And yeah, there's the Merkle tree. Okay. And if we come here, we try to fetch all the NFTs of this. Right now, our database has only one, so that's why it's just one. And let's just go ahead and mint some more compressed NFTs in the same Merkle tree, and our database should just keep on updating. Similarly, you can create more Merkle trees, mint more NFTs, and then you're able to index them and fetch differently. Again, done. And in our code, you can see almost instantly we get the response, and our database, it's minted, and our database should update. Where is it? Where is it? This one is it. There should be two. Yep, there's two. Awesome. And the owner is also the same. I'm sorry, actually I used the same metadata. We should have used some other metadata so that there are different NFTs. But anyway, so this is something that, how you can listen to on-chain data and index it and then expose it through APIs. This is just one use case. You can use it for your own protocol, all the transactions that are happening on your own protocol. And you can see one important thing, that you get the account data as well for this Merkle tree. So you can create an account indexer as well with this, not just a transaction indexer. Uh, yeah. So let's now try to implement compressed NFT transfer. And whenever an NFT transfer happens, our owner field should update. Right now, both are same. Okay, let's see how we can do that. So this is the transaction.actions array. We are going to find simple transaction.action. Since it's an array, we need to find the particular action, which is compressed NFT transfer. Here you go. And if you want to see the response structures, also very easily, you can check it out on translator. And if you open bubblegum, and if we check out, oh, compressed NFT, tensor C NFT, nice. Oh, yeah, man. Yeah, compressed NFT transfer. So let's just see what's the, so this is what you will get in the response. This actions array you will get. You only have 0 here, which the type is compressed entry transfer. And we're getting tree authority, we're getting the Merkle tree, sender, receiver, and NFT address. Awesome, that's all we need. And let's come here and let's go to handle transfer. Okay, let's try to implement this. And all we need is, it's actually very similar to handle mint, where we're doing console.log cnft transfer detected, and let's write down the action. That's it. And then we just need to update our database, our Superbase. Well, Superbase. And just copy this. Not from NFTs, and right now we don't need to insert, but we need to update. And what do we need to update? Where we need to update the owner to a new owner, but first we need to know the new owner, and it will be again, let's check this. Sender, so receiver would be the new owner, right? So we come here, we do action dot info, because it's like this, action, then dot info related to it. You also get the source protocol, address and name, info dot receiver. This is our new owner. But we also have to mention where it matches the NFT address is action.info. We get the NFT address. Yes, we do. NFT address. And hopefully that's it. So now, whenever a transfer happens on a Merkle tree, our database should also update. So you can imagine it like Firebase with a real-time cache of on-chain data. So whenever something changes on-chain, your cache automatically updates. Superbase from NFTs, update owner to this, match this. And where the NFT address is this. And yeah, awesome. Let's try it out. And let's also add the same logic, but for burn. Burn detected. And now we need to update. So we have a burn field as well in our which is null. Uh, okay, we should have a default value to it, which is 0. Let's just have 0 and 1 here. And we come here, then we burn to, now what's the response structure of burn? Let's check it out. We get tree authority, we get Merkle tree, we get owner, NFT address, update authority. Okay, pretty simple. So again, the same thing, just set burn to maybe 1. Your NFT address matches this. And that's it. Now, whenever we actually transfer, wait, we have to call this as well. Dot find compression of the burn, and then let's remove this. This is useless. And we will do handle burn, and then we transfer the CNFT burn action. Okay. Amazing. Our callback is still working. Okay. And yeah, cool. So we had minted this NFT, and let's try to transfer it now. So this is the NFT address. This is the sender. This is the receiver. This is the transaction. Let's try. Okay. Okay. Well, unknown sign. Different wallet. Yeah. Yep. Done. Let's check, and let's check our code. So we got the transfer. We got the callback. CNFT transfer detected. You can see, and this is the info. This is what we got. This is the new receiver. Let's see if our database is updated or not. Okay, it's there on blockchain. Where's our database? No. Okay. Why? Why? What did we miss? We come here, transfer action. Let's check logs once more. Transfer detected. CNFT transfer detected, which is here. CNFT transfer action is correct, and then we're just doing owner is REC. This everything is correct. Action dot info dot update owner is this. The match NFT address. Wait, this, and do we have this NFT address in our database? I think, yeah, it's the same. Okay. It's owner only. Okay, the NFT address is this. Let's try one more. Sender, receiver, NFT address, update authority we don't need. So all we're doing is handle transfer. Serve, let's make. Let's try this. Try this. Okay. Sorry. So let's try this NFT address. Okay. Same sender, receiver, everything is same. No, something is an issue here. Uh, hmm, I think something is happening. Uh, okay, compressed NFT transfer. Hmm. So, update PQ NFT address. See. Okay. Let's just try to mint another one. Ah, man, every time I forget. Yep, yep, done. Okay. And now our database should be updated. There should be three. Yep, it is. So basically, yeah, you can see that, as the transactions are happening, we are indexing it in our database and everything is running. I look into why compressed NFT transfer is not working, but we have only like 10, 12 minutes left. So just want to leave it for some Q&A. And I'll do one thing. I'll also put this code open in GitHub and share it with all of you. So you guys can basically experiment with it.
Yeah, awesome. Thank you. Yeah, Ish, feel free to send the GitHub link to me when it's ready, and I'll paste it and send it along to everybody in the hackathon. I'm sure that they will very much find it useful, and then they will build something useful with compressed NFTs. But yeah, guys, you heard Ish. If you've got any questions, now it's time to ask. Feel free to pop them in the chat. Feel free to pop them in the questions tab, wherever, and he'll get to them soon. In the meanwhile, I've actually got a question. So I could you get a little bit into compressed NFT use cases? What are some of the areas that you think that compressed NFTs could be used in a better way than regular NFTs? Is it gaming or the arts, or what's your opinion on that?
I feel definitely gaming is one thing, because if we talk about actual games, like World of Warcraft, Dota, and there are so many millions of players are using in-game items. And if we just start minting those in-game items as regular NFTs, it's gonna cost a bomb, and it basically inhibits masses to onboard, because it's like, okay, why do I need to mint, why do I need to pay so much amount? I mean, it's Solana, so it's already low compared to other chains, but it's still a significant amount if it's happening at mass. So definitely this is one thing. Then imagine e-commerce companies giving out compressed NFTs as the loyalty rewards. Maybe Amazon can do it. I mean, small users, small players can maybe do it with regular NFTs also, but still it's a significant cost to them. And it will always be in their mind that, okay, we implement this system, but what happens if we have to suddenly get a spike of thousands or 10,000 users? How do we handle that? So definitely any kind of space where there is going to be a requirement for mass usage, like e-commerce or brands or gaming, they can. Yeah.
Yeah, makes sense. We have a question actually in the chat. Augustine is asking, can we store our compressed NFT metadata on IPFS?
Yeah, you can, absolutely. I was just using the Mad Lads metadata URI, but I think this was here. And yeah, this is the metadata URI that I created. So just you can specify. Yeah. So if you remember, I gave a call to this metadata create API, and this is what we've gotten so far. And if I copy this and check it out, this is an actual IPFS link, and the image is also here in IPFS. Yeah, it's like a never-ending loop, but yeah, basically you can store the metadata on IPFS. You can store metadata anywhere you want, but it won't be there on chain. That's the only thing.
Um, cool. Thank you. I hope this answers the question. Yeah, Augustine, the code repo will be shared later on. I assume you don't have it ready right now, Ish, correct?
No, I
Okay.
just finished it before the call. That's why
Okay.
the transfer and burn was left. I thought I'll do it on the call, but yeah,
Yeah, sure. No problem. Then yeah, Augustine, I'll make sure to share the code tomorrow alongside with the video recording of the workshop.
yeah.
Next up, another question is, yeah, when you create compressed
You can
NFTs,
just
should
make
we
it.
store that transaction data in our own database like you showed, or could that also be handled by Shyft?
So this was to show you that you can do it, but eventually it's up to you. If there's a use case where you want to store it internally, and then maybe you want to associate that transaction data with some other features in your app, then you can do it. And if not, then maybe you don't need to store it. You can just fetch compressed NFT data directly through Shyft or any other provider. So basically, it depends on the use case that you might have. The reason why I was showing was just to show that how you can build indexing, how you can index on-chain data very easily using callbacks.
Cool. Yeah, that I think that very much answers the question. Next up, I see David typing. Okay, that's something else completely. But yeah, unless you guys have any final questions, I think we can slowly wrap it up here. Thank you very much, Ish, for coming and holding a wonderful workshop on compressed NFTs. I'm sure everybody enjoyed as much as I did. And yeah, guys, get building on Solana, get building on Shyft, and use Shyft. Shyft are actually giving a bounty for the
Yeah,
hackathon about which you'll find out on our website and in the hacker pack link previously.
yeah. And
Um,
just one information for everyone out there. So
Go ahead.
whoever takes up the shift bounty will not get eligible for the bounty price, but everyone participating will also get free paid plan for shift. And yeah, so go ahead and build.
Awesome. Yeah. Yeah, guys, you heard him. That's the ideal situation to have from a hackathon sponsor. We'll see you next on Thursday. Tomorrow there's no workshop, but on Thursday we'll be joined by Wormhole for the next hackathon workshop. Until then, thank you and see you guys some other time.
Yeah. So I
Bye.
think David is asking if shift
Oh,
works
yeah, we have
elsewhere
not. Yeah,
beyond
go ahead.
Sol. So if you're asking that if shift also supports other blockchains, then no. Currently, we're only live on Solana. Yeah, only on Solana.
Yeah.
Okay. All right.
Yeah, thank you very much once again, Ish, and thanks to everybody for coming and listening in on the workshop. See
Thanks.
ya.
Thanks everyone. See ya.